I did kind of mention yesterday the basic idea of calculus is finding the slope of tangent lines. So I'm going to revisit that before I get going. The overall idea is if you have a function, any arbitrary function, maybe it looks like this. The ultimate goal of calculus 1 is to find the slope of tangent lines. So if I randomly pick a position on this graph here, maybe right here, there's a tangent line, and the goal is to find the slope of that tangent line. There's a lot involved in what I just said there, really, because we're talking about a function. So chapter 1 actually just deals with functions. This should be kind of a review, but it deals with functions and terminology that goes along with functions, properties of functions like domain and range, something called continuity, so on and so forth. So we deal a lot with functions. Then we start talking about how to figure out the slope of the tangent line. It's called the derivative. And that involves something called the limit. Because the idea is, as I mentioned yesterday, there's only really one point we know on this tangent line. Assumption is we know the formula for the function. We know points along the graph of that function. And if we have a tangent line right here, we know that point. We know the coordinates of that point. So maybe it's like 5, 3 or something like that. But that's really all we know about the tangent line, is it goes through that one point. And if you remember calculating slope in the college algebra course, you've got to have 2 points. It's y2 minus y1 over x2 minus x1. It's the rise over run formula, slope formula. So we don't have that. So the idea is that you can approximate it by picking a second point out here somewhere. Or I should be pointing at function. It's not going to be exact, but it gives you an approximation. But then you could move closer, give you a better approximation, and closer and closer and closer. And as you keep getting closer and closer, that slope is going to approach some fixed number. We call that the limit. So we have to spend a lot of time talking about limits. That's a major concept we're going to have to talk about. And then once we do that, then we can start talking about the derivative. Derivative is just a word for slope of the tangent line. But then we're going to extend that to all types of functions. We're going to learn to calculate derivatives for all functions, all types of functions, and not only just at one particular point. The ultimate goal, I guess, is to find the derivative for any point along the original function. So if we got some original function, we want to find a formula for the derivative, slope of the tangent line, all up and down that original function. So that's calculus 1 in a nutshell. In chapter 5, we're going to learn just a little bit about the integral calculus. It's really more for calculus 2, but we do have a brief introduction at the end of the semester. But that's what we're going to be doing. So again, functions with functions, and we're going to talk about limits and then get into derivatives. So chapter 1. Chapter 1 deals with functions. The title is actually Functions and Models. Models just means modeling a real world situation with a mathematical formula. So in other words, word problems, really, describing some real world situation. The first section, 1.1, deals with different ways of representing functions and some terminology that goes along with that. The title is 4 ways to represent functions. Really, though, in this first section, they just deal with a whole bunch of miscellaneous stuff related to functions. It doesn't just deal with the 4 ways to represent, it deals with terminology like domain and range and things of that nature. But to kind of address this, there are 4 ways to represent functions. The main way to represent a function is with a formula. If I have a formula like this is a way to represent a function. The idea with the function is that you plug in some number and you calculate some related number. And this formula will do that for you. For example, if I plug in, I don't know, the number 4, randomly pick a number, let's say 4. I plug in 4. It just, hopefully this is just a reminder, this is function notation. This means the function has a variable x in it. Doesn't mean f times x, it means the function with the variable x. So when I write this, it doesn't mean f times 4, it means I'm plugging in the number 4 into the function. Wherever there's an x on this side, I'm plugging in a 4. So 4 squared is 16. 16 minus 4 minus 6 is 6. So when I plug in 4, I get 6, which can be written as over pair. I plug in 4, I get 6. And then I could just keep doing that with other numbers. If I pick something else for x, I'll do one more, I'll do 3. I could get another relationship. And I plug in 3, 3 squared is 9. And then 3 minus 6 more is 0. When I plug in 3, I get 0. And again, I could just keep going on and on and on. There's really an unlimited number of numbers that I can plug in and find the corresponding function. But anyway, that's one way to represent a function with a formula. But it also kind of showed another way to represent a function, just ordered pairs. This first number is related to that second number. 3 is related to 0. And then, of course, another way is to graph it. That is just another way to represent a function with a graph. Because with a graph, every point has an x coordinate and a y coordinate. So it has an x value related to a y value. For example, if I had a graph, maybe it looks like this. Any place I point on here has an x value and a y value associated with that point. It has an x coordinate, y coordinate. Maybe right there, maybe that's 1, 1. Where one over here, it's 2, 8. Right here, 0, 0. And of course, I could point a lot of different places as well, but they might be fractions or decimals. So I'm kind of picking nice whole numbers to illustrate what's going on. Anyway, that's just another way to represent a function. Now, a function is a relationship between one set of numbers called the domain with another set of numbers called the range. But not all relationships are functions. Here's the official definition. A function is a relationship between one set of objects called the domain of course, the objects usually are numbers. So it says we got this group of numbers, and those numbers are called the domain, and then they're related to another group of numbers. And another set of objects, the numbers of the range. So it's numbers related to other numbers, and then there's one important characteristic that will qualify it as a function, such that each object in the domain corresponds with, at most, one object in the range. Sometimes it sounds kind of confusing when you write down a definition like this, but what it's saying is each number in the domain only corresponds with at most one element in the range. To say it another way, each number in the domain cannot correspond to two different numbers in the range. So what if this is my relationship? 1's related to 3, 2 to 7, 0 to 7, and 5 to 9. Those four ordered pairs is my whole relationship. First, what's the domain? I can just list it out. It's all the first numbers. 1, 2, 0, and 5. Again, these ordered pairs are saying 1's related to 3, so 1 is one of the first numbers that's in the domain. Likewise, 2 to 7, so 2, 0 to 7, 0, and 5. It's just a list here. It doesn't have to necessarily be in numerical order. I'm just listing out the things that are used. Range, those are all the numbers that are being related to, so 3. 1 related to 3, 2 is related to 7, and then 0 is to 7 also. But I'm just listing out the things that are used. I already got 7 in the list. I don't need to put it in the list again. And then not. So if I list out all the numbers in the range, 47 and 9. And then the kind of the main question of that's is this a function? Now, for it to be a function, each first number can only be related to one second number. I can't have a single first number related to two different second numbers. So is it a function? The question, the confusion might be right here. I got 2 related to 7 and 0 to 7. I got 2 different first numbers related to the same second number. That's fine. That's not what this says. It says you can't have the same first number related to 2 different second numbers. But I can have different first numbers related to the same second number. So yes, it is. What if I had, this is my relation. 5 related to 7. 9 related to 18. 11 related to 10. And 9 related to 5. Now, here's another relation. It does have a domain and a range, but then the main question is it a function or not? First for domain. Well, the first numbers 5, 9, 11. And then there's another 9. It's already in the list, so I don't need to put it in the list again. I'm just listing out the things that are used. 5, 9, and 11. Range. All the second numbers, things being related to, so 7, 18, 10, 5. Yeah, I'm just listing them out. It's just a list, so they don't necessarily have to be in numerical order or anything like that. Just list them out. Then is this one a function? No. The reason is because of this. 9 related to 18 and to 5. I've got a single first number, 9, related to two different second numbers, 18 and 5. And all right, so in these examples, the function or the relation was just ordered pairs. What if instead you're given a graph? One, two, three. By the way, this thing I just drew, obviously, you've seen it before. It goes by a lot of different names. A lot of times I just call it the XY plane. Sometimes people will call it the rectangular coordinate system. Sometimes people will call it the Cartesian coordinate system, Cartesian coordinate plane, after Descartes. He's the guy that came up with this. He was a mathematician, but he was also a philosopher. So Descartes is somebody you may talk about in a philosophy class as well. In fact, he has a very famous philosophical statement that I'm sure you've all heard before, but maybe don't have it associated with Descartes. Does anybody know what famous philosophical statement he said, came up with? Yeah. Exactly. I think, therefore I am. I'm sure you've heard that before. I think, therefore I am. Descartes is the one that came up with that. And Descartes is also the one that came up with this. And I like to tell the story of how he came up with this, because it's kind of an interesting story. Descartes was not a morning person, but he felt like he did his best thinking in the morning. He felt like when he woke up, his brain was fresh and he could think clearly. He didn't have all the distractions of the day in his head. And so often he'd wake up and wasn't really ready to physically go about his day. So he'd lay in bed for hours and think about things. He did it, like I said, he felt like he did his best thinking. And he'd think about math and philosophy, so on and so forth. But it was one of those mornings and it was really cold and he saw a fly on the ceiling. It was really cold, and you know how flies are. If it's cold, they don't fly around a lot. They'll just kind of hang someplace, not fly around. So it was just hanging on the ceiling. But every once in a while, it'd crawl around. It wasn't even flying around, it was just crawling around. And it would move a little bit. Descartes realized I could describe the position of that fly with two numbers. And like with these tiles, it's real easy because if the fly was right there, I could say it's one tile that way, 1, 2, 3, 4, 5, 6 tiles that way. So 1, 6. But then when it moved, now maybe 3 tiles that way and 4 that way. So 3, 4. Then when it moved over there, 7, 9, so on and so forth. So that's the idea here. Any place you point, two numbers associated with it are pointed right there, 2, 2. But anyway, suppose we have a graph. Let's say it looks like this. Kind of like a circle, but it's a little longer. Like the ellipse when it's like that. It's centered at the origin. But this graph is describing a relationship between x values and y values. Anywhere I point, there's an x value and a y value. So it is definitely a relationship between x values and y values. A lot of them would be hard to read off precisely because they're going to be decimals and fractions. But for example, if I put right there, that's exactly 3, 0. It would be easy to find. I'll put right there, that's 0, 2. So on and so forth. But if I ask the question, what's the domain here, I could never list them all out like I did in those previous examples. Because in the previous examples, the whole relationship was just the ordered pairs that I put there. That's the whole relationship. The whole relationship this time has an infinite number of points. So I could never say the domain is 1, 2, 3. I couldn't list them out like that. But I could still specify the limitations, because there are some limitations. The domain, the x values, are always in between -3 and +3. The x values bigger than 3 are never used, and less than -3 never used. So I'd have to say it in a different way. I'd say the domain is -3, +3. Two different ways I could write that. I could write it with inequalities like this. -3 is less than or equal to x less than or equal to 3. Better way to read that is x is in between -3 and +3. Does have the or equal to part because it does hit the -3. Does uses the +3. And it gets everything in between. Like this point here might be, I don't know, 1.7, -1.5. This one right here is 0, -2. Another way to write it, though, is with interval notation, where you just write down where it starts and where it stops. It starts at -3 and stops at +3. -3 to +3. Now put those brackets on there to indicate that it actually does use the -3 and the +3. If I compare to inequality notation, it's got the or equal to part. With interval notation, that corresponds to a bracket opposed to a parenthesis. Anyway, the range corresponds to the values that are being related to. So those are the y values or y coordinates. Same thing, I could never list them out, but I could specify that they're all in between -2 and +2. So never goes higher than +2, lower than -2. So in inequality notation, the range, the y values, is in between -2 and +2. In interval notation, -2 to +2. And then really kind of the main question I was after here, is it a function or not? No, it is not. Because there are a lot of x values that are used twice. An easy one to see would be this right here. That right there is 0, 2. That right there is 0, -2. I've got the number 0 as an x value related to 2 and to +2. That right there is enough to say no, it's not a function, because it only takes one x value related to 2 different values. So no, it's not a function. But there's a whole lot more. A lot of them might be decimals, but maybe right here that looks like it might be 2, 1.3, and then down here 2, -1. So 2 is related to 1.3 and -1. Of course, the thing to observe with graphs is that they're above each other. One's above and one's below. They're directly above each other like this. For it to not be a function. A single x value means it's going to be moved to the right the same amount. Two different y values means one's going to be above the other. So a lot of times they just say, all you got to do is look for that. And the way you can look for that is imagine drawing a vertical line. If you could draw a vertical line that hits more than once, then it's not going to be a function. If I just draw a vertical line right there, hits here and hits here, same x value, two different y values. So they call it the vertical line test. You can draw a vertical line that intersects more than once. It's not a function. Of course, the same conclusion, but an easy way to do it for graphs. What about this graph? Does that graph describe a function? Yeah. Because I can't draw a vertical line that hits more than once. So you can use this to find out if a thing's not a function, but you can also use it to find out if a thing is a function. If you imagine drawing vertical lines, you can never draw one that hits more than once. If I draw one even right on the y-axis, I'm only going to hit once. These branches are getting steep, but still, if I draw a vertical line, it's only going to hit once. So we need a function. Yes. What about domain? I kind of went straight to whether or not it's a function, but of course it still has a domain and range, whether it's a function or not. What about domain? What would that be? The idea is? Yeah, negative infinity, positive infinity, everything. Because this graph goes left forever, so it uses all the numbers to the left, negative numbers. Likewise, it goes right forever. So in terms of the domain, the x values, negative infinity, positive infinity. That's how you'd write it in interval notation. There's other ways to write it as well. Sometimes you might see this capital R, weird capital R like that. It just means all real number, it means everything. It means everything. Now, what about range? Range corresponds to the graph the y values. Negative 2 to infinity. Because it never goes lower than negative 2. Both of those branches go up forever. So negative 2 to infinity. And you have to say it from bottom to top, smaller number to the bigger number. So negative 2 to infinity. It actually hits the negative 2, so it gets a bracket. So that just means it is included, the bracket. Actually, let me, before I do the next example, let me remind you something. What is this equal to? We could say the fraction 0 over 2, or I could say 0 divided by 2. They're equivalent. What's that equal to? 0. That one's not a trick question or anything. It's 0. 0 divided by just about anything is 0. What is this equal to? Undefined. Yeah, this is not a number at all. It's undefined. It does not have a definition of what it is equal to. It's not a number. It's undefined. This is kind of the thing I wanted to remind you. 0 in the bottom of a fraction is undefined. But kind of to be complete here, what would this be equal to? It has a different term. It's similar to this, but it's real close. Indeterminate, yes. Indeterminate. Indeterminate. Because we can't determine what this is. Because this rule up here says should be 0. That 0 on the top should be 0. That 0 on the bottom, it's 5. But we have both of them. Can't determine what this is. We're going to encounter that later, in particular with the derivative, and we're going to determine what it is for different situations. But anyway, I just wanted to remind you mainly of this one. Because if I have a function that's given to us as a formula, like this, I should point out that this is called function notation. So if I'm using function notation or if you see function notation, it is definitely a function, because it only applies to functions. But it plays the same role as the y in graphs. So if I've got a formula for a function like this, and you're asked to figure out the domain is assumed to be everything that can be calculated. It's assumed to be every single x value except for the ones where you wouldn't be able to do the calculation. Mathematically, you just can't do it. Are there any numbers in this situation where I would not be able to do the calculation? Because it would not turn out to be a number at all. Somebody said, I said, 2. 2 would cause a problem. Because if x were 2, I tried to plug in 2, 7 over 2 minus 2, which is 7 over 0. Undefined. Not a number at all. That's the only number that would cause a problem, because that's the only number that would cause 7 over 0. So the domain is everything except 2. Everything except 2. Everything except 2. I wrote it in words here. If you're asked a question like this, though, they're going to want the answer in interval notation. So the way to do that in interval notation is as follows. We want everything up to the 2, but not the 2. So parenthesis means up to the 2, but not including the 2. So right real close to the 2, like 1.9, 1.99, as close as you can imagine, but not the 2 itself. And then everything after the 2. So this gets everything before the 2 and after the 2, but skips over the 2. So that's the way to enter everything except 2 in interval notation. Squeeze in another one here. What would the domain of that function be? Now, the idea is the same. It's all the x's that you could plug in and you'd be able to do the calculation in terms of real numbers. Are there any numbers that I could plug in and I would not be able to do the calculation in terms of real numbers? Negative, yeah. Negatives are going to cause problems here because I can't do the square root of -9. If you've talked about complex numbers in the imaginary unit I, then you could do it in terms of that, but that's not a real number. In terms of real numbers, we can't do this. So they can't be negative. What they can be is 0 or anything bigger. Square root of 0 is fine, because square root of 0 is 0. And anything positive would be fine. I could calculate it. Although it might be a decimal, I could calculate it. So in this case, the domain would be all the numbers bigger than or equal to 0. Excess would be bigger than or equal to 0. Or in interval notation, 0 to infinity. Those are really the only 2 situations you need to worry about. Those are the only 2 situations where mathematically you would not be able to do the calculation. Can't have 0 in the bottom of a fraction. Can't do the square root of a negative. So if you don't have any fractions, x in the bottom, and you don't have any square roots, then the domain by default is just everything. One more quick example here. X squared minus x minus 6. No square roots, no fractions. So domain is everything, all real numbers. Negative infinity problem. Now it's the point where I really wish the projector would work. Because I want to show you a couple of problems from the homework. I'll do my best to reproduce it over here. Problem number 2 has a graph that looks kind of weird. So it's got a graph that kind of looks like this. And then they ask those basic questions. The first question they actually ask is it a function? Is this a function? When you got a graph, you use the vertical line test. If you can draw a vertical line that hits more than once, it's not a function. If you can't draw a vertical line that hits more than once, then it is a function. So if you imagine drawing vertical lines, for example, if I draw one over there, that doesn't hit at all. Definitely not more than once. Likewise, it doesn't hit at all. If I draw one that hits right, or comes down right there, it hits once. That's all I'm done. Yet not more than once. Likewise, all the way through here, only once. I guess kind of the tricky part is right here. Did that hit more than once? No. The reason it didn't is because that's got a solid dot, that's got an open or hollow dot. Solid dot means that's part of the graph, and open dot means it's not. So the graph is coming up, getting really close to that open dot, but that open dot itself is not part of the graph. So that vertical line still only hits one time. If I come over further, that vertical line only hits once. A little further. I kind of missed there. Didn't hit at all. That one hits once. But anyway, I cannot draw one that hits more than once. Either doesn't hit at all or hits once. So is it a function? Yes. Domains corresponds to the x values that are used. We need to list out or use integral notation to talk about the limits of the x values. First of all, I want to point out that nothing to the left of -3 is used. Graph doesn't exist to the left here. It starts at -3, it goes to the right. So nothing less than -3. Likewise, nothing bigger than 2 is used for sure. So it's not going into 2. And you can see it uses just about everything in between. The question is, what about here? Is it missing any numbers there? No, because again, the solid or the empty dot there, the hollow dot means the graph is coming up and getting very, very close, as close as you can imagine. but then jumps up here and picks up the -2. So it gets as close to -2 as you can imagine this way. And then the solid dot here, it hits exactly -2 and continues on. So even though there's this discontinuity, this jump here, in terms of x values, it doesn't miss it. So it uses everything from -3 to +2. The domain is -3 to +2. Range is slightly more complicated. First of all, though, it doesn't use anything less than the -3. The range, the y values, -3, it never goes lower than that. Likewise, it never goes higher than the 3. So it's definitely in between -3 and +3. From -3 to -2, no problem. But if you're looking at the y values, there is a small problem from -2 to -1. There's a jump. It doesn't use the stuff from -2 to -1. In fact, it doesn't even use the -2 itself. It just gets real close to it. So it starts at -3, comes up real close to the -2, and then there's a jump to the -1, it goes all the way up to 3. So to write that down, bottom to top. So -3, it uses the -3, it's a bracket. It comes up to the -2, as close as you can imagine, but it doesn't get the -2 itself. So the way we indicate that is with a parenthesis. That means as close as you can imagine to the -2. And then there's a jump. So there's another piece that goes from -1 all the way up to 3. When you have more than one piece, we use this union symbol. It looks like the letter U, but it's slightly different actually. But it means union, which means we got another piece. -1 to 3. It hits the -1, it uses the -1, and it uses the 3. So brackets with both of those. And solid dot there with the -1. It gets up to the -3 at this high point here. So they are included. About out of time. It's one more before we leave. Kind of similar to this one. Number 6 is this one. Square root 1 minus x squared. And that's what's the domain. That's the only thing we need to figure out. What's the domain here? There's a square root. It's the same idea. What's under the square root has to be 0 or bigger. Can't be negative. Can't be the square root of negative. Over there, it's just an x. So here it's a 1 minus x squared. So it gets a little bit more complicated. But to write it down mathematically, what's under the square root, 1 minus x squared, has to be bigger than or equal to 0. But write it down like that. What's under the square root, 1 minus x squared, has to be bigger than or equal to 0. Again, what's under the square root can't be negative, because if I plugged in something for x and I happen to get -5, square root of -5 can't do it. But if I plugged in something else for x and I happen to get +6, square root of +6, I can do that. Might be a decimal, but I can do it. So anyway, now that I set up this inequality, I need to attempt to solve it for the x. And there's a lot of different ways of doing that. But the basic way of doing it is first just change it to an equation and solve that first. Change it to an equal sign. Because it's so easier to solve equations than inequalities. If I just change it to an equals, then to solve it for x, I'm going to add x squared to both sides. And then to get rid of the square, I take the square root. But whenever you do that, there's a plus or minus when you do that on the square root principle. Plus or minus the square root of 1 equals x. Square root of 1 is 1, so x is plus or minus 1. X equals plus or minus 1 and negative 1. So those are the solutions to the equation. To solve the inequality, though, I need to go a step further. What this tells me, though, is this is the only places where it can change from being bigger than or equal to 0 to less than or equal to 0. So often what people do is test intervals. And this is not the only way to solve this. But it's kind of the main way that's used. We got -1 and +1. That's the only places where it can change from greater than to less than. So just pick a number in each interval and test it. So -2. If I plug in -2, is that bigger than or equal to 0? I get 1 minus -2 squared, +4. 1 minus 4 is -3. Is that bigger than or equal to 0? No. It's -3. It's less than 0. But -2 didn't work, so that means this whole interval, everything up to the -1 doesn't work. About -1 to +1. Let's try 0. Plug it in, see what happens. 1 minus 0 squared, is that bigger than 0? I plug in the 0. 0 squared is still 0. One bigger than or equal to 0? Yes. So since 0 worked, and it can't change anywhere in there, then that means everything in between the -1 and +1 is going to work. So -1, +1. Finally, after the 1, my test is 2. Plug that in. 1 minus 4. It's -3. No. -3 is not bigger than or equal to 0. So it's just -1 to +1. That solves this inequality, which corresponds to the domain then. So the domain is -1 to +1. It gets the brackets because at -1 and +1, it's exactly equal to 0, and square root of 0 is 5. Anyway, I'm out of time. I actually went over a little bit. I apologize for that. But tomorrow I'm going to do one more problem from this section, and then I'll move on to 1.2. That's all for today. Great rest of your day. See you tomorrow.